So here we have the differential equation exam from fall 2023. And it's the third exam, which means we're talking Laplace transforms, we're talking series, and that's the two things we're going to talk about because that's what the test is going to cover. It's going to be a good test, 6 questions, lots of fun. So let's take a few minutes and go over the questions and work through the problems. And of course, as always, we want to make sure we put our name on the test because if we don't put our name, we're not going to get the credit. All right, well, let's begin. Number 1, we're asked to find a Laplace transform, namely u of t minus 3, so this means that there's been a shift, 1/2 t squared plus 5 e to the power of 2t minus 1 plus 7 root t minus 3. Now, of course, as we're taking the test, we have some formulas handy. In fact, we have a whole sheet full of formulas. And looking at our formula sheet for number 1, one in particular jumps out. Namely, we have this rule that says if you have a u of t minus a times a function, you can handle it in the following way. Namely, you'll get an e to the minus as, and then you'll have Laplace transform of f of t. Not f of t minus a, but f of t. So where do we begin? Well, the key is we want to make sure that what's attached to u of t minus a looks like a function of t minus a. So that's where we're beginning this problem. Say, okay, so we want to make sure everything looks like t minus 3. Now, we have some good news here. We have 3 pieces. One of them is a freebie. Notice this part right here. It already has a t minus 3 downstairs. Nice. So what's that going to be? Well, we can think of this as 7 t minus 3 to the minus half. Now we're good to go. All right. Well, is there any other one that's not too bad? Yeah, the middle one's not too bad. What is that? Well, what do we have? The 5, of course, that's just a constant. So you can think this as 5e. And now what I'll do is where I see t, I'll put t minus 3. So that's 2t minus 3. But wait, that's 2 times t minus 3 is not the same as 2t minus 1. That's 2t minus 6. Aha! So what we'll do is we'll tweak it by plus 5, right? Because minus 6 plus 5 is minus 1. Or we could write this as 5 e to the 5th e 2 t minus 3. All right, well, great. That handles that one. Now we have one more, and that's the t squared. All right, so let's talk about this one. So we have a half t squared. Well, a half t squared is the same as a half, and now a classic will do a t minus 3 plus 3 squared. Yes? Minus 3 plus 3, 0. Of course it works out. So now we square this. So this thing, this is like a plus b squared. So this would be 1/2 a squared plus 1/2 in front times 2 times a times b. So the 1/2 and the 2 cancel. 3t minus 3. And then 3 squared times a half, 9 halves. All right, now what does this do? Let's put this all together. All together. Now, what do we have? Well, we can say, really we're trying to find the Laplace transform of u t minus 3 times, so the first part becomes a 1/2 t minus 3 squared plus 3 t minus 3 plus 9 halves. And then we have a plus 5 e to the 5th e 2 t minus 3. And then plus 7 t minus 3 to the minus a half. There we go. It fit on the paper just barely, but that still counts. All right. Well, now we're ready to say what happens. So the u of t minus 3 tells us we're going to get an e to the minus 3s, right? So u of t minus 3 becomes exponential. Now, before we do the next part, remember this piece right here, this is our f of t minus a. So this is f of t minus a, where, what is f of t? Well, to figure out f of t, everywhere you see a t minus 3, put in t. So it'd be 1/2 t squared plus 3t plus 9/2 plus 5e to the 5th e to the 2t plus 7t to the minus half. All right, now, how do we figure out what goes here? Well, for that, we say, okay, take the f of t, and now term by term, take the Laplace transform. So we say, all right, 1/2 t squared. Well, a half. Now, how do you do t squared? Okay, go back to the formula sheet. We have t to whole power, so that'd be 2 factorial over s to the 2 plus 1, 2 over s cubed. So 1/2 times 2 over s cubed. Okay, that's that piece. Plus 3. Now t, similar, 1 over s to the 1 plus 1, s squared. Then 9/2, Laplace transform of 1 over s. 5e to the 5th is a constant. Laplace transform of e to the 2t, well, that's also on our formula sheet. So e to the 2t, 1 over s minus 2. Okay, so 1 over s minus 2 plus 7. Now, t to the minus a half, well, that comes into this category here. So what is it going to be? Well, it's going to be a gamma minus a half plus 1 over s to the minus a half plus 1, which, by the way, is a half. Now, that's the end of the Laplace transform. Let's just make a quick note. This becomes gamma of a half. What's gamma of a half? Root pi. So say, so this piece right here, this is root pi. Okay, so let's just rewrite this one last time. E to the minus 3s. Half times 2, 1 over s cubed. 3 over s squared. 9 over 2s. 5e to the 5th over s minus 2. And then we have 7 root pi over s to the 1/2. And there we go. That's our answer. We're done. Woohoo! All right. So, of course, the main thing, make sure to rewrite it as t minus a. Understand what is f of t, and use the fact that it's linear, right? Linear says if you have a bunch of things being added or subtracted, just do them one at a time. Put it all together, life is good. And then we move on to the next problem. Number 2. Two-part problem. So we're going to find some inverse Laplace transform. So let's start with part A. The inverse Laplace transform, 1 minus s over 4s squared plus 1. Now maybe you think, partial fractions. And then you're like, oh, we don't need to do partial fractions. It's already been partial fractioned. What do I mean by that? Well, notice this doesn't factor any further without getting something complex. And it's already a quadratic. And so if you were to do partial fractions, you'd come to the conclusion, oh, wait, there's nothing to do. It's all done. So really, what's left for us to do? Well, we have to figure out what's going on. And we say, well, we've got that 4 there. That's a little bit annoying. Let's move that out. Can we do that? Well, sure we can. What is this? This is, we can pull out a 4 from the downstairs. And if we did that, we'll pull it all the way out in front. That's 1/4. And then we have Laplace inverse of 1 minus s over s squared, right, because I'm pulling out the 4, and I have to pull out a 4 here. So that's 1/4, which, by the way, is a half squared. All right, now we start thinking, what does this look like? Hopefully we don't have to think too long, because we've seen things like this. We've seen sine and cosine. S squared plus something squared. S squared plus something squared. And it doesn't have to be a whole number. It can be a weird number, like a half. Well, a half's not that weird. So we say, okay, if I have just an S, cosine, if I have that constant, sine. Say, oh, well, okay, what we can do is we can take advantage of something upstairs. And I'll point it out. It's called the minus sign. And you might like, what? Well, when you have addition or subtraction going on upstairs, you can pull things apart. So we'll pull it apart. So what does that say? We have 1/4 inverse Laplace of, well, 1 over s squared plus a half squared, and minus s over s squared plus a half squared. All right, well, are we ready? The second term, we're good to go. The first term, we have a half squared downstairs, so we need a half upstairs. Well, all right, what do? Well, we make it a half, right? That's the idea. If you need something, put it in, but then make sure to compensate. So we say, all right, we'll make it a half. Now there's lots of ways to make it a half, but the easiest here is to multiply by a half. And why is it the easiest? Because it's easiest to compensate. Here, I'll put a 2. Right? Because 2 times a half is 1. And now, life is good. Why? Well, what do we have? We have a 1/4 out in front. We have a 2. And then this is sine of 1/2 t. And that is cosine of 1/2 t. Or if you like, 1/2 sine of 1/2 t minus 1/4 cosine 1/2 t. And we're done with that one. We got a second one. Nice. All right. Well, let's go on and work on our part B. So here, inverse Laplace, s squared plus 1 over s plus 1 squared, e to the 4s. Now, this feels more like partial fractions. But before we do, partial fraction has to say, hold on. There's an exponential function there. What do we do with that? You can't do partial fractions unless it's polynomial, right? You have to be polynomial both top and bottom. Well, so what we're going to do is we're going to take that exponential, just sort of slip it off to the side. All right, so what do we have? This is the same as inverse Laplace of, we'll have s squared plus 1 over s times s plus 1 squared, e to the minus 4s. Minus, because it came from the downstairs, so when you move it upstairs, it's minus 4s, again, off to the side. All right, so now partial fractions. Okay, so we pause our Laplace inverse for a moment and move into partial fraction mode. So this would be s squared plus 1 over s times s plus 1 squared. Well, something over s. Now here we have s plus 1 squared, so we've got to build up to it. Something over a single s plus 1, and then something over s plus 1 squared. Right? Right. Yeah. Now, this is a place where sometimes people are like, shouldn't that be a cs plus d? Careful. Careful. The answer is no, because this, what you're looking at is the inside, s plus 1. That's what we would call linear, not quadratic, irreducible quadratic. Another thing is, notice how many constants should you have upstairs? Well, here we have 3. The number of unknowns should match the degree of the denominator you started with. We started with the degree 3, so we should have 3 unknowns. So this is right. Okay, so after we have our setup, and this is one of the hardest things about partial fractions, is making sure we get our setup right. The next thing is we clear our denominator. So we're going to have s times s plus 1 squared on everything. That leads us to s squared plus 1 is equal to a times s plus 1 squared plus b times s plus 1 plus c times s. Now, there's a couple options. You can do expansion, which is fine, and actually you can get quite a lot with that, or you can make good choices. You can get quite a lot with that. Now, I'm a person who likes to make good choices. So let me see if we can get all the way with good choices, or at least most of the way. So what's a good choice? Well, remember, it's a good choice is something which gets us 0. 0's a friend. And so we say, okay, now that doesn't mean always that 0 is a good choice. We want to make zeros. Well, fortunately for us, 0 is a good choice because that does make a 0. So if we plug in 0, we get 1 equals a, because 0 plus 1 squared is 1, plus 0b plus 0c. Aha! We've solved for a. A is 1. We're a third of the way. We have s plus 1, so let's plug in minus 1. So s equals minus 1. Minus 1 squared plus 1 is 2. So 2 equals, here we'll have a times 0, b times 0, and then c times minus 1. So minus c. Or we could say c is negative 2. All right, now we have a and c. So that means there's just b left, only one thing to figure out. And we could expand, or now we just make another choice. Let's make another choice. Let's plug in positive 1. 1 is an easy number to work with. 1 squared plus 1 is 2. 1 plus 1 is 2. 2 squared is 4. So this would be 4a. But what is a? A is 1. So this will become 4. Then we have b times 1 times 2, which is 2b. And now we have c times, which is minus 2, times s, which is 1, which is minus 2. And now what do you see? Well, 4 minus 2 is 2, and there's a 2 over there, so you end up with 0 equals 2b, or b is 0. Good, good. Now, that can happen. Sure, no worries. It's all right that we end up with some of our terms are 0. Okay, so now let's update where we're at. So we finished our sort of segue, our detour, if you will, into our partial fractions. So we say, look, this allows us to rewrite this as the inverse Laplace of, and now we're going to replace this s squared plus 1, s times s plus 1 squared, using this expression with our values for a, b, and c. So a is 1, so 1 over s. B is 0, so nothing over s plus 1. And then c is minus 2. So minus 2, 1 over s plus 1 squared. And then all that, e to the minus 4s. All right, good. Well, we've done a lot of the hard work. We still have to work out what's going on. We see an e to the minus 4s, and that brings us back to the same thing we looked at for problem 1. They really like this one. So e to the minus 4s says there's going to be a u of t minus 4. So we know that our answer will have a u of t minus 4. So let's go ahead, we'll put that on the back side, u of t minus 4. What about the rest? Well, let's, for now, not worry about this e to the minus 4s. Suppose we just saw these pieces. Well, 1 over s by itself would be what? Well, it would be 1. Inverse Laplace of 1 over s is 1. That's on our table somewhere. It's actually right near the top of our table. See, 1 over s, 1. Now, 1 over s plus 1 squared. Where did we do that? Well, because we have an s plus 1, that's a shift in the Laplace side of things, And that corresponds, when we see a shift on the Laplace side, that corresponds to our nice rule. And there's so many we have to take a second. Here we are. It's right out. See it in there. See it? The Laplace of e to something t, f of t, is a shift. So I say, oh, this is s minus minus 1. So this really came from an e to the minus t of 1 over s squared. Well, where do we see 1 over s squared? Well, that would be up here, where n equals 1. So the Laplace of t to the 1 is 1 factorial over s to the 1 plus 1. So we say, okay, so we have e to the minus t times t. All right? So the e to the minus t handles the s plus 1. The t handles it being 1 over that squared. Okay, and then the 2 comes along as a constant. Now, this part right here, this is our f of t right now. We want to have f of t minus a. So we say, all right, everywhere where we currently see a t, we put in t minus 4. So this will become 1 minus 2 e to the minus t minus 4 times t minus 4 times u of t minus 4. So there's that piece. And we're done. That's it. Good. Nice workout. But many problems still left to go. So let's keep going. Number 3. We're going to let f of t be a piecewise function. 1 if t is less than 2, and e to the t plus 1 if t is greater than or equal to 2. So we have two behaviors. There's the part that happens at the start, which is before 2, and the part that happens after 2. So which means there's a change. When there's a change, we use our on-off function, u. U is very popular on this test. So how do we do this? Well, we rewrite this in a way that's going to be convenient for us to work with. We start with, what's our initial behavior? It's 1. And then we say, well, there is a change in behavior at time 2. So we have change in time 2 means u of t minus 2. And now we say, well, what are we turning on? It's e to the t plus 1. What are we turning off? 1. So this is the same as 1 plus u of t minus 2 e to the t. Okay, good. So this is just rewriting f of t. All right, now what can we say? Well, we want to find the Laplace of f of t. The good news is we've done about a third of the work. Just by getting to this stage, we say, okay, well again, the rule for our unit step function says if we want, a u, t minus a, we have to make it f of t minus a. Okay, so lo and behold, what happens? Well, we're going to say this is the same as 1 plus u t minus 2 e t minus 2 plus 2, which is 1 plus u t minus 2 e squared e to the t minus 2. Okay, and now we're ready to go. So here we go. What happens? Well, we're going to take the Laplace of our 1 plus u t minus 2 e squared e to the t minus 2, which becomes Laplace of 1 over s. We see a u of t minus 2, e minus 2s. E squared is a constant. That comes out. Now, this is e of t minus 2. That is our f of t minus 2. So here, this is f of t minus 2, where f of t is e to the t. Say, okay, great. So what do? Well, what's the Laplace transform of e to the t? We use our rules. And the Laplace transform of e to the t is 1 over s minus 1. Now, if you like, you can put these together. So this becomes 1 over s plus, now here you can add and pull out a minus 2. You don't need to, but e to the minus 2 s minus 1 times 1 over s minus 1. Again, these are just combining these two exponentials. This is perfectly fine. This is perfectly fine. And you could also even say e to the minus 2 s minus 1 over s minus 1. Also perfectly fine. Look at all these perfectly fine answers. They are all perfectly fine. Okay, so there we go. Now that's part A. What about part B? Well, what do we have? We're looking for the Laplace integral from 0 to t cubed f t minus tau d tau. Well, does that look like anything? And the answer is, it does. It looks like that part right there. See how we have one part is tau, one part is t minus tau. You might say, well, wait, f is t minus tau in our problem. F and g are just symbols. Don't get caught up in symbols. Symbols can be changed. No worries. The important thing is what we have here. Integral from 0 to t. One part is tau, one part is t minus tau d tau. And that is convolution. Okay, so we're really doing a convolution. Now what's the rule say? If we're doing Laplace of a convolution, multiply the individual pieces together. So first off, what are our pieces? Well, this part, that's our t minus tau part, that looks a lot like our function f of t. What about this part? That's the tau part. What does that look like? Well, replace tau by t, and you get t cubed. So what's happening is we're really taking the Laplace transform of t cubed convoluted with f of t. The rule says this is the same as the Laplace transform of t cubed times the Laplace transform of f of t. All right, well that's good. Let's start with the Laplace transform of t cubed. Do we know that? Well, t to a power says, for example, n equals 3, 3 factorial over s to the 4. Now 3 factorial is 6, so this first part will be 6 over s to the 4th. Now how do we find the Laplace transform of f of t? Well, that's part A. So that's 1 over s plus e to the minus 2 s minus 1 over s minus 1. And we're done. That's it. That is the answer. Cool. So part B was all about, can we see the convolution? And if we can, life is good. Oh yeah. Number 4. A spring mass system with a mass of m equals 1, a spring constant k equals 9, no damping, and an external force of 12 cosine 3t minus 6 sine 3t. Okay. All right. I just noticed there's no verb in this sentence. Oh, thank goodness this isn't an English class. Whew. Okay, but the point is we have the spring mass system with all these parameters. Moreover, x of t, which is the displacement or motion of the spring, has some initial conditions. X of 0 equals 0, x prime of 0 equals 1. Set up the differential equation modeling this spring mass system and use the method of Laplace transforms to find x of t. All right, well, let's begin. Now, for a spring mass system, we have mx double prime, cx prime, kx equals our external force, where m is our mass, c is our damping constant, k is our spring constant, and external is the external. That's how you know what the external stands for. So in our case, m is 1, x double prime. C is 0 because there is no damping. See how it says no damping? That's our big clue. K is 9, so plus 9x. And our external force is given to us. 12 cosine 3t minus 6 sine 3t. And then we'll throw in some initial conditions. x is 0 equals 0, x prime is 0 equals 1. And now we have our beautiful differential equation set up. All right, we've done half of what it asked. I don't know if it's half the points, but we're halfway through what it's asked. Okay, now we have to use the method of Laplace transforms. You might say, wait, couldn't we have solved this using other tools? Yes, of course we could have, but we were told to use Laplace transforms, and we want credit, so we're going to follow instructions. Okay, so here we go, following instructions, because following instructions is one of our favorite things to do. We have Laplace transform of x double prime plus 9 Laplace transform x equals 12 Laplace transform cosine 3t minus 6 Laplace transform sine 3t. Whew. All right, well, let's see where this goes. Now, for x double prime, we again have our formula sheet, right? You should always have your formula sheet. That comes down to this part. S squared times the Laplace transform, what we're looking for. S, x of 0, x prime of 0. Okay, so x double prime, S squared capital X minus S x of 0 minus x prime 0. And then we have plus 9 capital X equals 12. And for cosine and sine, we have our equation sheet. So cosine, there's an s over s squared plus b squared, sine b over s squared plus b squared. So we're going to have 12. Cosine is the s over s squared plus 3 squared. That's s squared plus 9. Then minus 6. And then it's b, which is the 3, over s squared plus 9. All right, good. Now, there's 3 steps to doing our using Laplace transforms. There's the take the Laplace transform, which we've now done. Now we have to do the algebra. Well, okay, so algebra here just is mostly cleaning up. Now, we know a couple of things. We know x of 0 is 0. We know x prime is 0 is 1. Okay, so we're going to move, that's going to go away, and this 1 we can move across. All right, so what do we have if we continue our cleaning up? Well, we have our s squared and 9 times x. So s squared plus 9 capital X is equal to, well, here we'll have, these are both over s squared plus 9. We can put them together. We'll have 12s minus 18 over s squared plus 9. And then, don't forget, this becomes minus 1, comes over as a plus 1. So plus 1. Well, let's continue combining. So, okay, s squared plus 9, s squared plus 9. This would make it a grand total of s squared plus 12s minus 18 plus 9 minus 9 over s squared plus 9. Now, solve for capital X. Divide both sides by s squared plus 9. So we get s squared plus 12s minus 9 over s squared plus 9 squared. Ooh, ah, ooh. Okay, what are we going to do here? That's not just sine or cosine, because there's a square down there. Before we panic or rush to anything, go back to the formula sheet. Is there anything on the formula sheet that looks like s squared plus 9 squared? Okay, so we grab our formula sheet. S squared plus 9 squared. S squared plus 9. See, now this doesn't have the square downstairs. Wait, what? Oh my. There, look at it. You got an s squared plus 9 squared s squared. So you think of for a second, imagine, and to help us imagine, we'll write it down. Suppose we put in b equals 3. So this would become 6s over s squared plus 9 squared. And here you'd have s squared minus 9 over s squared plus 9 squared. So, okay, well that's something. Okay, so looking at that, well, we definitely have an s squared minus 9 going there. And, whoops, I should have been looking here. Okay, so, sorry about that. We definitely have an s squared minus 9 going here. And so, okay, let's pull that off. So s squared minus 9 over s squared plus 9 squared. That's perfect. Perfect. Exactly what we kind of want, because that's the formula. Okay. Now then there's this 12s. Look, you have a 6s. 12s versus 6s, that's like you have 2 6s over s squared plus 9 squared. And now, if I move this over just a little bit, we're like, what? This is nice on the formula sheet. That's nice on the formula sheet. It's all coming up nice. Okay, so we're ready to write down our answer. Here we go. So the answer, x, is the inverse Laplace of capital X, right? We're in our third phase. We did our algebra. We got it ready to do the inverse Laplace. We say, well, the inverse Laplace of s squared minus 9 over s squared plus 9 squared is t cosine 3t. The 2 is a constant. Inverse Laplace of 6s over s squared plus 9 squared is t sine 3t. And we're done. Nice! Oh, it came out to be a beautiful answer. It's like they love us. Of course they love us. We're one of their favorite students. And so they're going to give us problems that are solvable. Now, it doesn't mean they're trivial. No, they'd never do that. They love us too much to make them trivial. But we have the tools. And so it's a matter of being careful with the Laplace transform, being careful with your algebra, and knowing your table. Know your table. 4 out of 5 dentists recommend that you know your Laplace transform table before taking the third exam. Well, that's 4 problems for Laplace. There's 2 problems left. Time to get more serious about it. Number 5, our first series problem. We can tell it's a series because we see the sum. So that's a series. Remember, a series is like a big infinite polynomial. So we're given that y is a series, is a solution to x squared plus 1y double prime minus 3y equals 0. And we have some initial conditions. Y of 0 equals y prime of 0 equals 2. Okay. Now we need to find a recurrence relationship for the Cn, and we need to find the values C0 through C4. All right, good. Well, this should be fun. Okay, so what are we going to do here? Well, we see the words recurrence relationship. When we see the words recurrence relationship, we say, oh, okay, this tells us here we want to make one big sum. So that's our goal. We have one big sum we're after. Well, so how do we do it? So we're going to write everything as our big sum. We already know what y looks like. And so one thing we should write down is what is y double prime. So y double prime, well, that you come into here, and we say, well, that's like writing 2 derivatives. So what would happen is you'd take an n down, then the next time you bring an n minus 1 down, Cn x to the n minus 2. Okay, so that's for reference. So, first thing, we're going to replace our non-polynomial things, y double prime and y in this case, by this series, which is basically big polynomial. So everything's coming up polynomial. That's an underlying theme. When we talk about series, it's everything's a polynomial. And just like, okay, make it work, make it work. So we have our x squared plus 1y double prime, which, by the way, let's go ahead and at the beginning, right? This is x squared y double prime plus y double prime. And so we have x squared. This expression here, sum n equals 0 to infinity n minus 1 cn x to the n minus 2. Okay, there's our first piece. Plus y double prime, sum n equals 0 to infinity of n minus 1 cn x to the n minus 2 minus 3y, which is up here, sum n equals 0 to infinity cn x to the n equals 0. Okay, and this 0, by the way, is there, right? So let's recap. X squared y double prime plus y double prime minus 3y equals 0. Okay, good. Now, very quickly, let's take this x squared and move it in. And if we do that, what will happen is we combine and it becomes x to the n. Well, that's very convenient. Now we go through our process. Now, when I'm thinking about putting things into one big sum, I do 3 small steps. I make sure I do a shift, so all powers look the same. I do what I call peeling, which makes sure all starts are the same. And then once that's all true, combining. All right, so first off, shifting. Well, so I want everything to look like x to a power. I use my favorite letter. I use to the L because I think you can write a really pretty L. So here, well, our power is currently n, so we'll just say everywhere we see an n, we put an L. Here it's a little more interesting because our power is n minus 2. So we'll say, well, look, n minus 2 is L. Here, it's n equals L. So what do we have? Well, that's the sum, L, because we switched to L, 0 to infinity, L minus 1, C, L, X, L, plus. Now here, we have to think a little bit. So if I want L, n equals 0, L should be negative 2. So it's the sum, L equals negative 2 to infinity, and then L is n minus 2, or n is L plus 2. So L plus 2, L plus 1, C, L plus 2, x to the L. Remember, you got to change everything. It's the philosophy, the same philosophy that we encounter when we're talking about substitution and integration. Everything's got to be updated. Now the last term, that comes back to being just, oh, we're just changing our symbol. Like, yeah, change a symbol, no problem. Life is good, Bob's your uncle. All right, now we've done our shift. Next up, we talk about peeling. We look at our starts, 0, minus 2, 0. We want our starts to be the same, so we're looking at the 0. That's where we'd want to start. So we come up here and we say, okay, let's talk about what happens with minus 2. Well, plug in minus 2, you get 0. Oh, all right. Okay, what about minus 1? You get 0. Oh, okay. So when we peel off minus 2 and peel off minus 1, you peel off a 0 and a 0. Well, that doesn't do much. So you say, hey, we could just start this sum at 0. So here, peeling is very easy. You might say it's very appealing in this kind of problem. I know. You were just waiting for like, oh, Steve, you're just going to make a silly pun, aren't you? Of course, it just wouldn't be me if I didn't try. So here we go. What do we have? We're going to put it in one big sum, combining. So L equals 0 to infinity. And we have 2 pieces that involve just the CLs, and 1 piece that involves CL plus 2. Let's start with CL plus 2. So we have L plus 2 times L plus 1, C, L plus 2, plus, here we'll get, well, we can write it as L squared minus L from there. And now this piece Don't forget this minus 3. Don't forget that. We've been very careful to keep writing it down. It comes in as minus 3CL, x to the L. Now, again, the L squared minus LCL, that's from the first sum. The minus 3CL is from the last sum. And all that equals 0. Well, the 0, on a side note, what does that really mean? This is the sum of L equals 0 to infinity of 0, x to the L. It basically says when you have the 0 polynomial, it just says all your coefficients are 0. And two polynomials agree if and only if all their coefficients agree. So you're like, ooh, well that tells us that all these coefficients of x to the power L, and that's why, by the way, we put all this work was to put all the coefficients together. That's what we've been doing, is grouping all the coefficients together. And when you realize that that's what you've been doing, it's like, that's not so bad. It's not as scary. Sure, there's some work, but it's like, okay, group stuff together. I'm on board. So the punchline, this equals 0. In fact, it equals 0 for L greater than or equal to 0. Now, we essentially have the recurrence relationship here. But let's write it a little bit more explicitly. We have L plus 2 times L plus 1 CL plus 2 plus L squared minus L minus 3. Unfortunately, that doesn't factor in a nice way, but that's okay. That's life. CL equals 0 for L greater than or equal to 0. Now, that's our recurrence relationship. You could also rewrite this in a slightly different way. Namely, if you solve for CL plus 2, you could say, well, CL plus 2 is, you'd move that across, so you get a minus L squared minus L minus 3, CL, and then divide by L plus 2, L plus 1. And that would be for L greater than or equal to 0. Okay, so these are both options. Okay, so now we have our recurrence relationships. Good, good. Well, we're half done. Actually, we're more than half. We've done all the hard parts. What's left? Well, we've got to find the values C0, C1, C2, C3, C4. We're going to split this into two ways to find. There's the first two, C0, C1, and then there's the remaining three. Now you might say, well, why divide it that way? Well, C0, C1 we're going to do by initial conditions. Okay, so what do we have? Well, we have that C0, that's equal to y of 0, and y of 0 is equal to 2. C1, that's y prime is 0, and that's equal to 2 as well. Okay, so the first coefficients come from initial conditions. We're priming the pump. How do we find the rest? Well, the answer is we look at coefficients. So in particular, when I'm looking at coefficients, I'm really, for C2, this is the coefficient of 1. C3 is the coefficient of x, and C4 is the coefficient of x squared. So we're looking at those coefficients, the constant coefficient, coefficient of x, the coefficient of x squared. Well, so let's go with our coefficient of 1, our constant coefficient. And for that, well, that's in our sum, because our sum starts at 0. So we say, okay, L equals 0. We can use our recurrence relationship. Either form, they're both fine. And, well, might as well put it into here. We have, everywhere you see L, put a 0. C2 equals minus, well, 0, minus 0, minus 3. So there's a minus 3. Downstairs, 0 plus 2, 0 plus 1. So that's the 2 times 1. And then times C0. Well, minus minus makes plus. So we have 3 halves. C0 is 2. So that's 3 halves times 2, which makes 3. All right, well, we got to move this up, and because we need space. What about L equals 1? All right, well, let's do L equals 1. C3 equals, okay, you have 1 minus 1, 0. So we have a minus 3. Now down here we have a 3 and a 2. So, okay, 3 times 2. And then times C1. A minus minus makes a plus. The 3's cancel. C1 is 2. 2 over 2 cancels. So we really have here, well, this is 3 times 2 over 3 times 2, which is 1. All right, good. So there's C3. Now, what about C4? Okay, L equals 2. C4 is, well, minus, now I have to be a little bit careful here. We have 4 minus 2 minus 3. All right, you already see an L put a 2. Downstairs we have 2 plus 2, which is 4. 2 plus 1, which is 3. Then we're timesing it by C2. So 4 minus 2 minus 3, that's 4 minus 5, which is negative 1. And there's a minus. So we end up with a 1 over 4 times 3. What is C2? Well, C2 is 3. So the 3's cancel, and we end up with 1/4. All right, good. So let's write them all together, making it easy for our grader to spot and give us points, right? Because we want to make sure our grader gives us lots of points. We're all pro points. So we have 2, 2 from our initial conditions, then 3, 1, and 1/4 from using our recurrence. And there we go. There are our coefficients that we needed to find. Good. A little bit more to write down, but philosophically, we're grouping things together, and life is good. That brings us to number 6. And it's another series question. So we're given that y is a series, is a solution to e to the minus 2xy double prime plus 1 minus 3xy prime plus x squared y equals 2 over 1 minus x. This looks really complicated. Definitely compared to what we've talked about. It's like, but okay, all right. We also have that y of 0 equals 6, y prime of 0 equals 4, and we want to find some coefficients. Now, part of the way we're going to approach this is to say, well, what aren't we finding? Well, we're not finding recurrence relation. That's good. And so we say, okay, well, we know a couple things. We know we're going to get a few pieces from initial conditions. So that's the C0, C1. Those will be initial. And then we're going to get the rest from looking at coefficients. C2, C3, C4, where we really say, well, which coefficients do we need to look at? And the answer is we say, well, we need to look at the coefficients of 1, x squared. So now our great thought is, oh, let's make all our pieces look like polynomials, and then we're going to group and say, what's the constant term, the coefficient for x, and the coefficient for x squared. And doing that, we'll get our answer. Okay, so before we get too far along, let's go ahead and at least make sure we get our point or two. That comes from identifying the c's, 0 and c1. So c0, that's y of 0, that's 6. All right, we're getting credit. Cool. c1, that's y prime is 0, and that's 4. Okay, so we'll have that for reference. Now remember, everything's polynomial. Everything's polynomial. Okay, so let's start with the y. Well, we know what y looks like. Well, that's y. That's we have our big sum. Sum k equals 0 to infinity, ck x to the k. Now, when we see the y, we notice it's attached to x squared. We say, okay, well, since it's attached to x squared, how much of y do we need to look at? Not very much. Actually, the only thing we need to look at is c0, because since we're multiplying by an x squared, that already gets it up to c0x squared. Everything else is higher power, and so we don't worry about it. And so that's the dot, dot, dot. All right, what else do we have? We have a y prime. Cool. Y prime, well, that's our sum, k equals 1 to infinity of k, ck x to the k minus 1. Now that's equal to, well, plug in, I put in 1. That's a true statement. I'll put in 0. Plug in 0, you get 0. Plug in 1, you're going to get c1, x is 0. Plug in 2, you'll get 2c2 x to the 1. Plug in 3, you'll get 3c3 x squared, and everything else is x cubed or above. We don't need to worry about it. Now, what do we do with this 1 minus 3x? The answer is we like it, and we don't need to worry about it right now. Why? It's polynomial. Our goal is we want everything to be polynomial, and that already is. Nice. Okay. All right. We have a y double prime. Okay. So y double prime. That's our sum. K equals 0 to infinity of k minus 1, ck x to the k minus 2. Okay, plug in 0, you get 0. Plug in 1, you get 0. Plug in 2, you get 2 times 1 times c2, and then x to the 0, so 2c2. Plug in 3. 3 times 2 is 6, c3x. Go one more. Plug in 4. 4 times 3 is 12, c4 x squared, and then everything else is higher power. Okay, are we done? No. What else do we have? Well, we have these functions, e to the minus 2x and 2 over 1 minus x. So let's start with e to the minus 2x. Well, good news, we have a formula sheet. And on that formula sheet, you'll notice there's some rules. So we say, oh, e to the something is the sum, something to the k over k factorial. So in our case, it's the sum, 0 to infinity of, so z is minus 2x. Minus 2x to the power k over k factorial. And yeah, there we go. Yeah. So what does this equal? Plug in 0. Minus 2x to 0 is 1. 0 factorial is 1. 1. Plug in 1. Minus 2x to the 1 is minus 2x. 1 factorial is 1. So that becomes minus 2x. Plug in 2. Minus 2x squared is 4x squared. 2 factorial is 2, so that's plus 2x squared. And then higher power stuff, which we don't care about. Isn't it great to say, and we don't care about? Now, not that we don't care about math. We love math. But for us, let's see, what do we have? The last piece, 2 over 1 minus x. So, oops, 2 over 1 minus x, that's 2 times 1 over 1 minus x. Say, well, wait a second. 1 over 1 minus x, well, that's the sum, k equals 0 to infinity of x to the k, which, don't forget the 2, looks like 2 plus 2x plus 2x squared, dot, dot, dot. So, what's the punchline? Every single term here becomes a polynomial. That's the idea. That's the whole idea. And now we just are going to write it out. And so let's start. We'll start with our left-hand side. Okay, so e to the minus 2x. That's 1 minus 2x plus 2x squared times y double prime. 2c2 plus 6c3x plus 12c4x squared plus 1 minus 3x y prime. C1 plus 2c2x plus 3c3x squared plus x squared y. Well, plus c0x squared, other stuff. All right, good. Now, here's the step. This is the important part. So all of this was to say, hey, we're going to replace by just enough. Everything's polynomial. Now we're going to expand and gather. So take your time. We have time. We're doing great on time. And we say, all right, let's start with our constants. Well, how can we get a constant? We could get 2c2 from the first piece. And that's the only way to get a constant from multiplying two series together. Here you'd have to choose the constant and the constant, so now that would be plus c1. And, well, there's no constant there, so that's all the constants. Okay. Now let's talk about x. So how do we get an x? Well, from here we could multiply constant times x, so that would be, whoops, sorry, not, that looks like an equal, so that should be a plus. Plus, and here we have 6c3 minus 4c2. Okay, so bum, 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 bum. All right, now how do we get it? Here, 2c2, right, 1 times 2c2x minus 3c1. All right, and that's it. Plus, now x squared. All right, 12c4 minus 12c3 plus 4c2. Okay, that's our terms here. Over here, we can get a 3c3 and a minus 6c2. All right, boom, boom, and then we have to stop. And finally, a plus c0 x squared. All right, good. Well, let's clean that up a little bit. So this is 2c2 plus c1 plus, well, here we can group the middle terms, 6c3 minus 2c2 minus 3c1x. Here we have 12c4 minus 12c3 plus 3c3 minus 9c3 plus 4c2 minus 6c2 minus 2c2, and then a c0. Yeah. I was like, there's no c1? Yeah, there's no c1. Doesn't have to be. All right, great. And that's times x squared. And then everything else is higher order. We don't care about it. Now, remember, that's the left-hand side. Whoops, left-hand side. Equals the right-hand side. Equals this stuff. So, equals 2 plus 2x plus 2x squared and other stuff. All right. Well, that's great. So what does that tell us? Well, it gives us a series of equations. And in particular, we can say, hey, 2c2 plus c1 equals 2. Now, it's so high up here, but look, we know what c1 is. c1 is 4. So 2c2 plus 4 equals 2. 2c2 equals negative 2. So c2 is negative 1. We got it. All right. Well, now on to the next term. We have 6c3 minus 2c2 minus 3c1 equals 2. But we bound c2. That's minus 1. So that's 6c3 minus 2 times minus 1 makes a plus 2. then minus 3c1, and again, we know c1 is 4, so we have minus 12 equals 2. Well, the 2's cancel, so 6c3 needs to equal 12, so c3 is 12 over 6, which is 2. All right, great. Now we go to the x squared. 12c4 minus 9c3. Well, c3 we just found, that's 2. So minus 18. Minus 2c2. Well, c2 is minus 1. So minus 2c2 is plus 2. Plus c0. c0 is 6. Okay, so plus c0 makes a plus 6. And that's here equals 2. Well, again, the 2's cancel. Minus 18 plus 6 is minus 12. Move it across. We get that 12c4 equals 12. So c4 equals 1. All right. So we're done. We just have to put it together. So our list of coefficients are c0 equals 6, c1 equals 4 from initial conditions. And then from expanding and comparing coefficients, c2 is negative 1, c3 is positive 2, and c4 is positive 1. So 6, 4, minus 1, 2, 1. And that's it. There's the answer. Now you're probably like, that was work. It was work. You know, once or twice we should do some work. And this was one of those once or twice times. But the concepts, the ideas, they're not bad. It's just we have to be careful. Work with your algebra. Don't rush. Group coefficients. We're okay. You're okay. I believe in you. With practice, this becomes more natural. Even maybe a little bit easier? I think so. All right, well, thanks for joining me. Hope you did well, or I hope you're going to do well, whatever it is, and hope to see you again. Bye.